Assalamu alaikum, guys. This is chapter number 7 of digital hardware course, last chapter. It's not a full chapter, but some topics related to the memory and programmable logic devices we are going to discuss here. So let's see now what we have. So starting with the memory. So before just going into detail, I'm just revising you what is a memory, guys. So we have seen that a single flip-flop, okay, can store a 1-bit information. All right. Uh, if you want to store a group of bits all together, then what we need? We need a register. And what is a register? A register is a group of flip-flops that can store a group of binary bits, basically. Okay, so it could be 4-bit, 8-bit, 16-bit, 32-bit, and so on. So that is a register. All right. And now just think as a memory. So when we say the word memory, it means we have a multiple registers. All right, we have a multiple registers where we can store and each register can store a group of bits we have seen, right? So now this time we have many locations where a group of bits can be stored in each register. The number of bits a register can store is also called as a word. Okay, so we can say, okay, one word is stored there, one word is stored there. So in order to understand the memory, I think you can also take an example of your notebook, okay, which have single line notebook. So in a notebook, when you look at this hard copy of the notebook, you can see that there are a single page. On a single page you have multiple lines, right? So on each line, for example, if you are using mathematics notebook, in each line you will be having the squares there also, right? It means each line is having multiple, many squares. Let's suppose there are 8 squares there. It means is that each line is correspond to a single register, and each square in that line is correspond to a single flip-flop. So you have now multiple lines on each page of your notebook. Similarly, in the computer memory, we have multiple registers, right? So each register is capable to hold the data, right? And we can read that data, we can write that data, right? So we can access that register to read the information. We can access that register to write the information. Are you getting? So because of we have a multiple registers on each page, so we must tell the memory which register I am going to use to perform read or write operation, right? So there must be what you called, there must be a strategy to identify or to give the address of each register so that we can tell the memory I'm going to use this particular register. For example, we have 8 registers, right? And each register can store 8 bits. So if you have 8 registers, so we have to tell the memory unit, I'm going to use which particular register out of 8. 8 means, okay, we can numbering from 0 to 7. So we need to tell the memory, I'm going to use register number 7 to perform read operation, to perform write operation, whatever, right? Any one of them we can perform. So there must be a requirement of address of the memory. So the point is that we have, as I just mentioned, how many registers we have in my example, what I am saying, 8, and each 8 register can store 8-bit information. So let's just look in a way. We have something like this, right? So 1, 2, 3, 4, 5, 6, 7, and let's suppose 8. All right. And each register, let's say register 0, register 1, register 2, register 3, 4, 5, 6 and 7 registers are there, right? So how would I tell the memory that I am going to use this particular register? So we should have a addressing technique. All right, so in order to have a different address, how many bits I need so that I can have a unique address for for every register, like 8 registers are there. So you know that already. If you use 3 bits, yani 2's power 3, we can generate 8 different combinations. And what will be the 8 different combination? It could be 0 0 0, 0 0 1, 0 1 0, then 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. It means 0 to 7. So this is the unique address of each register, guys. Now, so we have called this one address, and this is your memory. And each memory can have, as I said, 1 2 3 4 5 6 7 8. For example, 8 flip-flops. So register size is 8-bit, means we can store 8-bit together. So we will be having input lines which will be 8-bit input lines, so that we can store the information. Then we'll be having 8-bit data output line, 8-bit data output line to read the register. So we call this one address lines. Okay, 3-bit address line. We have a data line, okay, that brings the data to the register, that take the data from the register. So these are the things which is basically required. So hope you get some idea by this explanation, that what is a memory and what are the address lines and why do we need the address lines. Okay, what are the data lines that brings the data to the register or take data from the register, right? Let's move in detail. So the major categories of the memories, guys, are basically RAM and ROM, which is very common, and every one of you remember this one. Yeah, you must be knowing. So random access memory basically perform both operation. What is that? Read operation and write operation. But we have a ROM, which is read-only memory, where we can only perform read operation. We cannot write that one. So these read-only memory is basically a programmable logic device. These are programmable logic device. See, the information is stored in the ROM. We can read that one. That's why we are calling read-only memory. But somehow the information is going to be stored there, right? That's why we can read something. So depending upon the stage on which we can store the information or program the ROM, based on that we have a different categories of it. We'll be discussing later on these things. So these ROM is made up of basically programmable logic arrays, so that you can store your program. And these programmable logic arrays basically are it could be a programmable array logic, we call PAL. It could be a field programmable gate array, which is called the FPGA. Okay, so programmable logic devices are of different type. It could be programmable logic array, it could be programmable array logic, and field programmable gate array. So they are different array technique used by the programmable logic devices, like the ROM devices. Okay, we'll be discussing in coming time more detail about the ROM. So let's move first array logic. So array logic, it a different, little bit different from the conventional logic symbols. We'll see now here. So a typical programmable logic device may have 100 to millions of gate interconnected through a 100 to 1000 of internal path. Because of the information stored in the ROM, it is a lot of information can be there, so that the one of the famous ROM we call the BIOS chip, which is basic input output chip, which is on the motherboard, which basically have a subroutine for the when you first start your computer, so related to the booting and all your configuration. So every information is there. As you turn on the supply, that is in subroutine start executing one by one, and it works. So these these programmable logic devices may have millions of gates which are interconnected. It means there will be a lot of wiring, here. So how can we show this design on paper? That is going to be very difficult task. So for that purpose, we use this array logic symbology. Okay, it is a bit different from the conventional symbol basically. So see this conventional symbol of the OR gate, which have 4 inputs. Okay, but when we talk about the array logic symbology, we show the single line here, and then we have a multiple here inputs here. Depending upon which particular input is high, there will be a cross. Which is low, there will be no cross. For example, there is a high, there will be a cross. We'll be discussing all in these things in detail. So this is the conventional symbol. This is called the array logic symbol. We'll be using this one for the design. Then you will understand in detail. So just to show you, we have a conventional symbology, which you already know, and this is the array logic symbols. So first start with the random access memory. So the memory which you can read, which you can write. So memory unit store binary information in a group of bits. As I said, any group of bits mean a register, or which is called the word also. Okay. So in a memory, we can have multiple words to be stored there. So the communication between memory and its environment is achieved through a data input. I told you data inputs, like we have data input lines, output lines, address selection lines. Okay, then control lines, control that tells, are you going to perform read operation? Are you going to perform the write operation to the memory? These address lines could be n bit long. As I said, n is the number of bits that a register can store simultaneously. So let's suppose n is 8, for example. So the size of these data lines will be 8, so that 8 bits can go there and a register can store 8 bit. So register size is 8 bit, or we can say the word size is 8 bit. Similarly, if the register size is 8 bit, so output will also be 8 bit long. So 8 bit will be here. And then we have here k address lines. So k address lines means we know that 2's power k will tell you number of addresses present, right? If I say k is equal to 3, so 2's power 3 is equal to 8 address. It means 8 different registers can be located by using 3 binary bit, because we can generate 8 different addresses, right? So the memory, we can say now, it consists of 2k words or 2k registers. And if I say k is equal to 3, it means 8 words or 8 register. It means is that, and each word or each register can have n bit per word. Are you getting? N bit per word means, which I show you here already. This one, same example. So we have 8 registers or 8 words, and each word is basically 8 bit in size, like this one, right? This is the meaning of that one. That's why what we are saying, 2k memory and memory words, right? And bits in each word, which is written here. You can see this one, n bit per word. It means is that. So for example, if we have a 1k words, yani 1k registers, all right, and each register can have 16 bit each. This is the question. So 1k words, k guys, kilo, and you know the meaning of k, 2's power 10, and 2's power 10 means 1024. It means is that, it means they are saying 1k words, and this much of words or this much of registers. It means is that, and each register can have 16 bit each. So if I ask you how many bits can be stored in that memory, so I can say 1024 registers, and each register can have 16 bits. So this much of bits that memory can have. It means is that this much of bits, right? This memory can have. So in short, uh, we are representing this one in bits. We can also represent in terms of byte. You know that 8 bits is equal to 2 byte. So these 16 bits can also be written as 2 bytes. Means 1024 cross 2 bytes. It means is that, right? It means is that. So we can also say in terms of bytes, this much of bytes. So different ways of saying this one. So 1K and 16-bit means 2 bytes. The memory can accommodate 2K bytes. 2K bytes. Why they are saying 2K bytes? If we just bring down now. So 1024 means K multiplied by 2 bytes. So we can also write 2 and K, 2K bytes. Yani this memory can hold total 2K bytes. Okay, it means is that. Let's look in more detail the same memory we were discussing here. So this is the memory content, which is n is equal to 16. These are the 16-bit, yani each register can have 16-bit. And how many registers we have, how many words we can have, last word will be 1023 because of its mention the address is 10 we are using here because of we have 1024 different registers. How many? 1024 different registers. That yani now I want to find how many bits I need to have 1024 different addresses so that I can assign unique address to each register. So this one can be written as 2's power k, and that will be 2's power 10. It means k value will be 10, means I need 10 bits, 10 binary bits to have total 1024 different addresses. So first address will be all 000, next will be all 000, last will be the 1, and the last address will be all 10 bits will be 11111. If we read in decimal like 0, 1, 2, last will be 1024. Why 1024? Because last address will always be 2k minus 1, means 2's power 10 minus 1, which is 1024 minus 1, which is 1023 address. This is the address. So this memory content 1024 registers or words, and each word is 16-bit long. So we call this one 1024 into 16 memory. Okay, so each word in memory is assigned to an identification number called the address. Starting from 0, last will be 2k minus 1. K is the number of address lines, as I explained to you already. You must also know the meaning of kilo, mega. So this is about the kilo, 2's power 10, mega, 2's power 20, giga, 2's power 30. If I want to say 64K, so we can represent this one. 64K means 64K. K is here, right? So 64K. So 64 can be written as 2's power 6 multiplied by how we write the k, 2's power 10. You know that in a product the powers are gonna be sum, so 2's power 16. So 64k can be written as 2's power 16. It's just to let you know. Okay, so different way of representation of the kilo, mega, giga we can have. Let's move next. So the type of memories, guys, could be volatile and non-volatile. Like, so the memory unit that lose the stored information when the power is turned off are said to be the volatile, like the RAM, both static and dynamic. And now RAM is of two types, static RAM and another one is called the dynamic RAM. Okay, so two categories are there. So here, this is about the volatile memory, yani RAM. Another one is ROM, non-volatile memory, such as magnetic disk. ROM retain its stored information even after removal of the power. We'll discuss now volatile memory, yani static memory and dynamic memory. So static and dynamic memory. So static RAM, or in short we call SRAM, consists of initially internal latches or flip-flops, is the basic building block of these memory. Okay, and the stored information remain valid as long as power is applied to the unit. Because it is a volatile, definitely it will be valid as long as the power is there. It has some characteristic. What is that? It has shorter read and write cycles. It is faster, because we have seen that flip-flops are very fast because they work on the edges. It has low density, low capacity, high cost, high speed, and high power consumption. So these are the characteristics you must know. Maybe it can be asked anyways. Okay, so it is like static RAM. Then we have a dynamic RAM. DRAM store the binary information in the form of electrical charges on the capacitor. So here the technique of storing the information is in the form of capacitors. Okay, so how can we form the capacitor in the memory? So we use here MOS transistors. MOS transistors means it is called metal oxide semiconductors transistors. So MOS transistors are here. So this is, you already studied the BJT in electronics. This is another category of the transistors, which is called the MOS transistors. It is made up of semiconductor technology, and it consists of two metallic plates that act as a capacitor. So the charge information is going to be stored in the memory in terms of charges, basically. Okay, so the capacitor tends to discharge. We know the tendency of the capacitor. With the time, the charge goes discharge. So there is a need of refreshment. Just refresh this memory. So that with the time, it must be periodically recharged by refreshing the dynamic memory. So for the DRAM, we must basically periodically refresh the dynamic memory, so that the charge which is stored there on the MOS transistors must retain, but must not decay. If it is decayed, it means what happened? We will lose the information even if there is a power. Okay, so we must refresh that one. That is something different from the static RAM. So DRAM offers reduced power consumption, larger storage capacity in single chip memory. So basically, your RAM in general, which we called for the computer related RAM, these are DDR, DDR2, DDR3, DDR4 nowadays present. So these are all dynamic RAM. The cache memory, maybe you have heard this name, cache memory, this one is made up of static RAM, okay, which is faster, but it is costlier also compared to the DRAM. Okay, so it has some characteristic: high density, high capacity, low cost, low speed compared to the SRAM, low power consumption as well. So these are the characteristics of the DRAM, dynamic memory, random access memory. So now we can say what is volatile memory, which is RAM. There's two types, static and dynamic. Now, non-volatile. So ROM, as I said, ROM is also classified in different ways depending upon when the information is going to be written in the memory. Okay, so we have ROM, mass programmable, EPROM, EEPROM, flash memory. We'll be discussing all these things in detail. So just look the design of the ROM first. A block diagram of the ROM is shown here. It consists of K address inputs and N data outputs. So here we have only data outputs. We don't have this time data inputs. Reason, we can perform read. We are not going to write anything. That's why this part is missing compared to the RAM. So this is not there. So we have a K address lines so that we can generate 2's power K different addresses. We have memory enable. Just need to enable, because we don't need read and write. Only we need write. So we are saying this signal is now memory enable. Just enable and read the information. So we can say it is a 2K cross M memory. 2K means this much of words, okay, this much of registers, and each register can have M data or M bits basically. So this is 2K. Earlier it was N. Now we are using this time M here. So read-only memory design we are going to discuss. This is the conventional symbol, guys. We have seen that using the decoder circuit, I told you, we can also design any what you call function, okay, provided you must know the min terms. So for example, if you have here a decoder, so that for example 3 to 8 line decoder. So one, we have 8 out. So any particular will be high, will be getting here output. We have seen this one, how a decoder can be used for to implementation of the function if we know the minterms. So this is the conventional simple. But if we use array logic, these things become very simple with the array logic, because we here will be using a single line, because I told you why we use the array logic, so that we can represent the complex internal structure of the memory in a simplified way by not having a lot of wires, instead reduced one by using array logic symbology. So which particular input is connected out of this and a decoder, we can see here we'll be using a cross sign to just show this is connected with that, this one is connected with that, this one is connected with that. So we don't need to show 4 lines. This way we are reducing these lines 4 to only 1 by using array logic symbology. Look now, read only memory. Now I will be using how this k address lines is gonna be decoded now. So we are going to use here a decoder which consists of 3 to 8 line decoder. So you have a 3-bit address lines, and as I said, 2's power 3 means 8 different address can be generated. So for that we need a decoder which is here, and then it will be generating 8 different, and these are corresponding to register 0, register 1, register 2, register 3, and register 7. All right, and this is the data which is coming from the registers. Okay, this is connected here, and it is an OR gate. You know that if any input is high, output will be high, and this is the memory enable. So this is the design of 8 cross 4. 8 cross yani 8 registers or 8 words, 8 words or 8 registers, and each register is capable to store 4-bit information. That's why we have 1, 2, 3, 4 here OR gates. All right, let's see next now. So here we are going to see how can we read the ROM, stored information. So we can see here cross cross. These cross means the 1 is stored there, and wherever you don't find the cross, it means 0 is stored is there. So look here now. So when we say 8 cross ROM, we are just going to read each address. So we are going to read what is the stored at address 000. So when you give here 000, you already know that the output of this decoder is going to be the 1. Rest of them are going to be 00. So it is highlighted. It means is that whatever the value here, because there is no cross, you will be reading here 0. There is no cross, you will be reading here 000. So what is stored at this point? This is the data 000. Similarly, we can check for the next one 001. So when we say 001, it means this time this is going to be the high, rest will be 0. So this is the cross. It means you will be reading 1 this time. This is cross, you will be reading 1. This is not cross, 0. This is cross, like 1 you will be reading. So what is stored at address 001? This one. Same, you can understand. So cross means 1 and not cross means 0. So these cross basically are the fuses in actual ROM memory. This is provided with the help of fuse. Fuse you may have seen maybe at your home, connections, electricity connection at home. There are some fuses, whenever there is a high load or short circuit, that fuse blows. Okay, so this is like that fuse. They are joining 2 wires, yani this one with that one. So we are showing this one with the cross connection. So this is how to read the memory, how to read the stored information in the ROM. So other than this, ROM can also be used to design the multiple functions, same as the decoder. So we have seen already how can we use a decoder to design a function. We can also use the ROM implementation to for example, implement the 3 different functions. So we have given 3 different functions, and they are asking you use the ROM-based circuit implementation and design this one. So for the design of any function or implementation of any function, we must know the minterms, as I said. So you can see this is not a canonical form, standard form. So we must convert it for all the functions into the canonical form and find the minterms. Then we'll be going for the next step. So first step is to convert into canonical form and get the minterms. After getting it, we can see here the maximum minterm is here 7. So we need a decoder which is 3 to 8 line decoder, right? So that it can generate 0 to 7 outputs. 3 inputs, because of we know that maximum value is 7, so we need 3 inputs here. 3 inputs. Now because of we have 1, 2, 3 functions, so we use here 3 OR gate only, and we have done this thing already in a chapter number 4 using decoder how to function. So here we use multiple lines for each connection, like this one, like this one, like this one, like this one. We have to have something like that. But if we are using ROM implementation, so we don't need that one. We'll be using the array logic symbology. So look here, 0. So we'll be having here. Next one is 1. Connect here 1. 7. So this is 7. Cross here 1. So this is for the F. Same for the G. 0. So for the 0, cross 3. This one. 6. This one. 7. This one. That's all. This is about the G. Same for the H. For the H, 1, 3, 1, 0, 1, 3, 5, 7. Okay. So 0, 1, 3, 5, 7. That's all. So this way, we use a single decoder and ROM design concept, and we use the array logic symbology because of its mention, use the ROM design. So we can have this design. But guys, don't use this array logic symbol, okay, in the design of chapter number 4. You must use the conventional symbol design. This one, array logic, you can use only chapter 7 related questions like ROM design and all, because it is specifically for the ROM design, okay, for memory concept. It's not for the chapter number 4 or chapter number 4 combination circuit design. Don't use it there. Okay, so if it is coming here ROM design, then you can use a single line and cross connections. Otherwise, don't use with the chapter number 4. So now come to the type of the ROMs. As I said, depending upon when the information is going to store in the ROM, we have a different categories. So first category is called the mass program ROM. Mass program ROM. Yani, these ROMs have the or programmed during the manufacturing, okay, stage. Yani, a company needs some chips, so they tell that okay, we need this chip, and this is the data we need in each on each chip to be stored. So it provided to the manufacturing company. Then due to manufacturing, they stored that information, and it comes to that it comes with a ready stored information there. That is called the mass program. Second category is called programmable read-only memory. Okay, so this read-only memory, PROM, yani, it basically facilitate the researchers, a programmer, to program its own code or its own program instead of during manufacturing. So it is like one-time programmable. So how it comes like a we have all the locations by default. Each location is stored 11111 like that. 11 means they everywhere they are cross. So cross means there are fuses connections everywhere. For example, like we have this data 4-bit. So this is like stored information, and how it is stored everywhere. It's gonna be cross yeah, by default. Okay. Now, depending upon your program, the stored information you may have, for example, first is 1111, so that is fit. But for next word which you are want to store in the RAM, it's like ROM, it's like this way. Second one is like this one. So how will be doing this one? So there is a hardware called the burner, and we need a software also. So we put that chip on that burner, and then we fed this program. So what happened? That blow up these fuses. So this is done with the help of this cross, done with the help of fuses, as I just mentioned. So this burner blow up this fuse. So it removes these cross connections basically. Removing means any 0 is stored. Okay. For example, third one. So we need not this one. So it will blow up. This will blow up. Blow means the fuse will break here. When it is break, so there is no connection. So this is the technique used in this PROM basically. Okay, so programmer can store its own program. Third category is the erasable programmable read-only memory. It uses different techniques and it facilitates the programmers to reprogram the same chip for limited number of times. Let's say 10 times, which is erasable programmable read-only memory can be erased. Okay, and how will be erasing the information? By exposing this chip to the ultraviolet light. So if we give this one, the stored information will remove, and then we can reprogram it. But again, limited number of time. Let's say 10 times. Then next category is basically EEPROM, electrical erasable read-only memory. This technique, I think, we are using in the flash drives, which we are using. So multiple times, 100 to many hundred times, we can, store the information, format it, reuse it. It's like that. Erase the required data using an electrical signal. So the mean of erasing the information is the electrical high current instead of the ultraviolet light, which we use in EEPROM. In EEPROM, we use the electrical signal and current passed and stored information will be erased, and then we can rewrite this one. So this is about the different type of the ROMs. With this way, we have done with this chapter. Okay, so this way we end this the syllabus, which is the by this chapter, which is memory and programmable logic devices. So